engagement with the U.S. Department of Energy and with industry to advance the development of strategic U.S. infrastructure and capabilities. Jeff has held a long career in the nuclear industry. He holds nuclear patents. He has been involved in the fuel group business development with Framatome. Jeff holds a business degree from Averett University. Jeff, I'm going to turn it over to you.
Great. Thank you, Julie. And I appreciate being on the panel today with Simon and Peter and Dom. And I'd just like to start off by emphasizing the tremendous contribution that their companies are making in advanced nuclear, and consider it to be a privilege on the panel with them today. There's a lot of effort and energy that's being focused on the deployment of new reactors for commercial nuclear energy and their value to a clean economy. I'm encouraged for what it's going to be that's going to mean for the new products and solutions, and especially what this is going to mean for the workforce of tomorrow. And I would just like to say it is great to see so many students on this today, because you have a great future ahead of you, and it's glad to have you in this conversation today. During past panels, I've talked about Framatome's experience with high temperature gas reactors, and one of my favorite topics, the high assay LEU, which is really fuel with increased enrichment that's going to be needed by a lot of the different advanced reactors designs. But for today, I'd like to talk about a journey of success and what that could mean for us. After the 2011 accident at the Fukushima Daiichi nuclear power plant, I believe that it started a pivot for our industry, and that pivot, I think, is what ended up being a more urgent journey, in that we were challenged to expedite the research, the development, and the design of nuclear fuel products that would provide even greater safety and greater margins. And for us at Framatome, we engaged relatively quickly in the accident tolerant fuel program with the Department of Energy. We're now deploying what we call our Protect fuel in both PWR and BWR reactors. The first success that I see there in this journey was there was a very quick alignment with both industry and government, including fuel product providers, the industry working groups, the licensing body, congressional voices, the Department of Energy, and in our nuclear space, a relatively short time frame, a program was put in place that was very well aligned and prioritized. And with the government investment, it's a success that's benefiting and continue to benefit the existing fleet. The second success that I see, though, is that throughout this period, the value of nuclear energy and the innovation of folks like NuScale and Kairos and Terrestrial, the things that they have been working on, it was not discounted, but instead the various stakeholders have begun to realize that we can benefit even more from the deployment of small modular and advanced reactors. And so I think of NuScale's licensing approval as a great marker along the way on this journey. I can't remember a time when we've had this level of support for nuclear, with at least 10 projects awarded by the Department of Energy and for demonstration deployment, the reduction of risk, and the international opportunities that are facing us now. We're on a journey that we must succeed at for advanced nuclear. I don't know about you, but when I travel, I like to de-risk my trips. Where are the high traffic areas? What could cause a delay? Where should I plan to refuel? What flight alternatives are there if there's a delay or cancellation? And what have I learned from past travels that I can apply? So I've reflected on that as it applies to our risk on this journey of advanced nuclear, and some of the risk that we can plan for. And I'm just going to mention 3 of them here for our conversation today. But the first one is the risk associated with construction. We can really apply the lessons learned of those who have gone before us and look at how they have approached site construction and what they learned from that, and then strongly also encourage the workforce development that's going to be needed to deploy and construct a new fleet. And we have reports that are being produced that I think will help with that roadmap. I'm in the middle of reviewing a report from NEI, and there's others out there as well. The second risk, though, that I see along the journey is our supply chain. We currently do not have a robust supply chain for what I call the major components that are going to be needed in these nuclear plants. And folks like NuScale are having to rely on resources outside the U.S. to help shore that up for them. But I think we can use this as an opportunity for us to have the hard discussions on what's it going to take to invest, putting those capabilities in place so that we can be prepared for our future needs. And so instead of making this a detour, let's pave a road, so to speak, that will allow us to be able to have that supply chain in place. And the third thing that I thought about as a risk is a perceived risk, and that is operational experience with these new reactors. The plants are different, but yet they have more passive and inherently safe features, and they have great promise. But we need to build and operate those first plants to be able to demonstrate that confidence, and that is going to take time. But I think we have a good story to show our confidence, and having experienced utilities like Excel and Energy Northwest and others that are part of these deployments, that will help us build a good backlog for new plants. So let's build billboards along the way to tell our story of our success stories, so to speak, so that we can build upon those. So let me finish by saying Framatome's here. We are working with a lot of these different companies. We consider ourselves very fortunate to have our voice in this discussion. Our ambition is to help see these new reactors deployed and new products like fuel for NuScale, and to bring our expertise from our design school to help de-risk this journey. And I look forward to my son, who's a 16-year-old considering going into nuclear, to see a whole new fleet of reactors that will be there that will be servicing for decades to come. So the important point is that, like ATF, I think we'll succeed when we're aligned, when we're on the same journey, when we're working with each other, we're capitalizing on our expertise from industry and government, and we can weather these storms ahead and de-risk the deployment. So thank you for letting me be a little bit more reflective today, Julie. And I look forward to discussions with my counterparts here and for the journey ahead. So thank you.
Thank you, Jeff. Great discussion so far. Next, we're going to hear from Peter Hastings. Peter is the Vice President of Regulatory Affairs for Kairos Power. Peter leads teams responsible for licensing and permitting activities with the U.S. Nuclear Regulatory Commission, risk-informed safety analysis and probabilistic risk assessment, quality assurance, and government affairs. Peter has a lot of experience prior to joining Kairos Power. He's consulted with EPRI, with the Nuclear Energy Institute, the Nuclear Innovation Alliance, Tennessee Valley Authority, Southern Company, and several advanced reactor developers, both on developing a regulatory framework and the risk-informed licensing modernization project. Peter earned his BS degree in nuclear engineering from North Carolina State University. Peter, I'm going to turn it over to you. Thanks.
Okay, thank you. I've got some slides to share. Let me know when you see those.
We see them. Thank you.
Okay, great. Good morning. Let me start by thanking Jeff for that great introduction. We obviously knew what each other was going to talk about, but I was really taken by Jeff's very inspiring remarks, and I agree that pathway to success is what this should all be about. I am delighted to be here this morning. I'm going to give you an overview of what Kairos Power has been up to, and hopefully demonstrate that the challenges that Jeff mentioned can be addressed, are being addressed, and that there's not only a viable path forward for advanced nuclear to contribute to clean and reliable power, but that there are folks out there actually making it happen as we speak. Kairos Power is a mission-driven company, and we're singularly focused on that mission, which is to enable the world's transition to clean energy with the ultimate goal of dramatically improving people's quality of life while protecting the environment. To address the challenges that we've discussed, we clearly must deploy technologies that are safe. That's the price of admission for nuclear, but also affordable. And for Kairos, we intend our plants to be cost competitive with natural gas. Here's where we're located physically across the country. Our headquarters is in Alameda, California, in a repurposed World War II era hangar on the former Alameda Naval Air Station. This space houses about 50,000 square feet of office and lab space, including our rapid prototyping and technology development lab and our at-temperature molten salt lab. I run the Charlotte office, which focuses primarily on licensing work. Our second largest presence is in Albuquerque, New Mexico, where we're developing a component testing facility, an integrated engineering test unit, component manufacturing capability, and a fuel development lab. We had the pleasure of hosting New Mexico Senator Martin Heinrich and Secretary of Energy Jennifer Granholm at this facility not long ago, and I think it's fair to say they were impressed. We have a strategic collaboration with Materion, who's the preeminent provider of beryllium for our flag coolant, excuse me, in Elmore, Ohio. And our most recent addition is the Hermes site in Oak Ridge, Tennessee, which I'll discuss more in a moment. Kairos is an ancient Greek term for the right or opportune moment. And for us, that moment is the upcoming retirement of really a dramatic amount of natural gas assets. We believe this will drive a huge demand, and with the urgent need for non-carbon emitting technology, we believe we can help meet that demand. Of course, as I mentioned earlier, that requires that we think differently so that we can, in fact, be competitive with natural gas on a cost basis. We won't have time for a deep dive on the Kairos technology, but just a brief overview. So ours is a bit of a hybrid design. We use triso fuel, which was originally developed for high temperature gas reactors that Jeff spoke about. This fuel is resistant to neutron radiation, corrosion, oxidation, and high temperatures, and in fact has been demonstrated not to melt at temperatures that exceed our operating temperatures by hundreds of degrees. We also use a molten salt coolant, which was initially envisioned for molten salt reactors whose fuel is actually dissolved in the coolant. Our coolant, which is a fluoride beryllium lithium mixture known as FLIBE, has a really high heat capacity, so it's good for high temperature applications. It maintains a single phase throughout our operating range. In other words, it doesn't boil anywhere in our operating range. And it has a tremendous affinity for holding on to radionuclides in the unlikely event that they do escape from the fuel. We also maintain a near atmospheric pressure in our primary system. So that eliminates the volatilization component of say, high energy line breaks in higher pressure systems. The result of this combination is a system that reduces the likelihood of accidental releases really quite dramatically. And as a consequence, doesn't require large pressure retaining containment buildings. Here's a brief history of our company. We're coming up on our 5th anniversary later this year, but we really made a remarkable amount of progress in that time. We emerged from a DOE-sponsored integrated research project with the goal of commercializing the fluoride salt-cooled high-temperature reactor design. We're currently just north of 220 employees, almost all of whom are focused on the commitment to design, license, and demonstrate this technology, excuse me, through an iterative development and demonstration program. Our schedule is to deploy a test reactor by 2026, a commercial reactor before 2030, and a significant ramp up in deployment shortly thereafter. Early on, we began developing actual hardware in our prototype lab, kicked off significant pre-application engagement with the Nuclear Regulatory Commission. In fact, to date, we have over a dozen topical reports either approved or in review. And in the category of what we did during a global pandemic, we've commissioned the lab facilities that you see here. We've acquired and built out a component test facility and initiated construction of an integrated test platform, the engineering test unit. In Albuquerque, we've established a strategic partnership with Materion. We acquired and began characterization of the Hermes reactor site in Oak Ridge, Tennessee. We began construction of the component test facility in Albuquerque. We received a DOE Advanced Reactor Demonstration Program Risk Reduction Award. We began construction of a prototype fuel pebble lab, and we established a cooperative development agreement with TVA. The majority of the hardware that you see discussed here and on the previous slide has been developed or commissioned just in the past year or so, including development of many aspects of the Albuquerque facility virtually from scratch, from bare ground. Additionally, in just the past few weeks, we've submitted a construction permit application to the NRC, capping a very active and productive pre-application engagement. And all this occurred only a little more than a year after making the decision to insert a test reactor into our development cycle. So we went from the decision to do a test reactor to a construction permit application in under a year and a half. And I have to say, having been in this business nearly 40 years, that pace of development is really breathtaking. A connection back to two of the issues that Jeff raised, and I agree, the ability to achieve cost-effective and timely construction is really essential, and the supply chain for new and advanced reactors is also critical. For our part, Kairos Power's approach to develop this technology actually bakes these issues in as considerations. Our development is based on rapid iterations with actual hardware to the maximum extent practical. We find that this larger number of smaller iterations resulting in multiple design, build, test cycles better informs the design through production of actual hardware that in many cases helps to prototype the final design. Actual hardware iterations incrementally inform not only the design, but also the cost. So our test facilities are intended to culminate in a user facility, or the U facility, that not only will act as a training facility for our future customers, but also will largely prototype the actual commercial reactor by constructing it as if it were a reactor, which means that before we build the first commercial unit, we'll have a much more precise idea of the cost and effort to perform that construction on the actual commercial plant than we think has ever been achieved. So as I scroll through some additional pictures of the facility in Albuquerque, I'll address what we're doing about supply chain challenges. Adopting the approach that SpaceX and others have used, our hardware iterations also rapidly exercise the supply chain. And at the risk of maybe sounding abrupt, if we find the supply chain isn't up to speed on a given component, we fold that aspect of supply into our own vertical integration strategy. We've had success both in supplier partnerships and in building our own stuff. So we've included component manufacturing capacity into our Albuquerque facility. Our willingness to take on a greater level of vertical integration does a lot to address the supply chain risk. There are many components that represent cost and schedule risk for a new plant, including vessels, piping, and in our case, graphite, and even fuel. We've opened the aperture on our vertical integration strategy to consider items that others won't have considered in the past. So I'm going to close with a look at the Hermes site at the East Tennessee Technology Park, which was the former site of a Manhattan Project era gaseous diffusion plant, and also pointers to where you can go for more information. You can visit our website at kairospower.com. You can visit the virtual open house that we established in support of a recent public outreach meeting in East Tennessee at kairospower.consultation.ai. Thanks very much. That concludes my remarks.
Thank you so much, Peter. Great photos. Our third speaker today is Dominic Claudio. Dominic is the Director of Sales for NuScale Power. For the past 3 years, Dom has led the sales initiative for one of the world's leading small modular reactor designs. His entire 30-year career has been spent in sales. Dom has served with Areva, which is now Framatome, for 16 years, and he was Vice President of Annexio US for 5 years before he came to NuScale. Don holds a Bachelor of Engineering degree from the Stevens Institute of Technology. Turn it over to you, Dom.
Thank you, Julia. Appreciate that, and I also appreciate the opportunity to be part of this panel. And I would add that I very much listened with great interest to the panel that preceded this on hydrogen, and I'll try to tie some of the comments I'm about to make to that hydrogen story. I think there's some synergies there that might be useful. So let me try to share my screen. All right, so I'll touch on 3 topics, but again, I'll try to weave into this some of the comments that we heard earlier and tie it into the larger narrative. So I'll talk a little bit about the company, a little bit about the technology, and a little bit about the applications that are available as a result of this technology. So first, just a little bit about the company. Who is NuScale? NuScale was formed in 2007 for the sole purpose of completing and commercializing the small modular reactor. And what we call that is the NuScale Power Module, or NPM for short. What's also a couple of other noteworthy data points are that this technology, at least the way that the technology is used, has a lineage that goes back to the year 2000 as part of a DOE program where passive safety systems and natural circulation were being investigated. And that's a large part of the premise about passive safety systems. It also leads to cost reductions and generally a better and safer technology as it relates to small modular reactors. In 2011, Fluor became our lead investor, and that was a very notable event for a number of reasons, not the least of which was they certainly came with a significant amount of funding, and to something that we heard earlier from the standpoint that it does take vision, it does take a certain amount of boldness and audacity to go into these arenas because they are long lead time and long sales cycles. And Fluor became that investor, and they saw that vision, and they're very well positioned now as an owner of NuScale. The second notable part of that is that Fluor is a world-class construction company. And to the extent that they evaluated the NuScale design for constructability in the early phases, as the design was being promulgated, that it will pay its dividends from the standpoint that it's a de-risking element as we get into the construction and deployment of the technology. Next data point, 2013, NuScale won a competitive DOE funding opportunity award from the DOE. That was about $400 million. About $400 million has been provided by the DOE in a cost matching point of view. To date, NuScale has about over 560 patents. We're about 450 employees, 5 offices in the United States and 1 in the UK. And the final two significant data points is that in August of 2020, NuScale did receive from the US NRC design approval. And just to give a sense of what that means is the application for the design approval took over 2 million man hours in order to create, and the review of that application required another 1 million man hours as far as supporting and demonstrating to the NRC what was required in order for them to view the demonstrations required in the approval. So that level of work was about $750 million in order to satisfy the requirements of the US NRC and to gain that design approval. To date, the total investment in NuScale is about $1.3 billion at this point. So a little bit about the technology. So we spoke about the NPM, the NuScale Power Module. It's an integrated module that's factory built. It includes the reactor core, the reactor vessel, the reactor pressure vessel, the steam generators, pressurizer, and containment. Again, this is one integrated module, factory built. And what's significant about that is that, again, from the standpoint of minimizing the amount of time and the amount of expense in building a nuclear power plant, this work, the work to fabricate this module, is done in a factory in parallel to the civil work that's done in the field. So traditional construction schedule, at least a construction schedule for a NuScale deployment from the point that the first safety-related concrete is poured till commercial operation date is about 3 years or so. You can probably double that, if not a little bit more, for a traditional gigawatt-sized plant that has to have both the civil works and the nuclear steam supply system built in series in the field. So this is a significant evolution from the standpoint of making nuclear power more affordable. So we talked about the module. That's the picture on the left. It stands about 75 feet tall and about 15 feet in diameter. And what we do is we place these modules into a building that's submerged in a pool of water. And that, again, supports the safety case. Each module is capable of producing about 250 megawatts of thermal energy, and that's translated into 77 megawatts of electricity, as each module is affixed to its own unique power conversion system. And why that's important is it speaks to flexibility, it speaks to load following. At NuScale, and I think most of the participants in trying to find reliable carbon-free energy moving forward, believe that we're in an all of the above point of view when it comes to various generation sources. So when we talk about load following, what that means is that to the extent that you might have wind and solar in your grid, when the sun's not shining or the wind's not blowing, this configuration can support almost a minute-by-minute response to that wind and solar so that the grid stability is maintained. In the picture that you're seeing above, that's our flagship configuration. That's the configuration with which we went to the US NRC. It can house up to 12 modules. In total, that would be 924 megawatts electric gross. But smaller configurations can also be accommodated, whether you want a 4-module building or a 6-module building, or you can have a 12-module building and put in lower numbers of modules as you go along. You may start with, say, 6 and then graduate to 8, 10, or 12 as the need requires. The other thing that bears mentioning, and this ties into what was discussed earlier as far as cogeneration, you could dedicate some subset of these modules to electric production, a second subset to hydrogen production, and say a third subset to process steam or district heating. So there's a lot of flexibility that's afforded to you because you have a steam producer hooked up to its own power conversion system, or that steam can be utilized to support other needs. Again, what was maybe mentioned earlier is that this plant is walk-away safe from the standpoint that it requires no operator action, no AC or DC power, and no additional water in the event that you're in a situation that would require something beyond normal operating procedures. The other thing that's noteworthy, and we'll touch on this a little bit later, is that with TVA, we were able to demonstrate a methodology that supports an emergency planning zone to the site boundary. And that's a difference and an evolution relative to a gigawatt-sized plant that would have typically a 10-mile radius around it supporting emergency planning zone. So the picture on the right shows the reactor building in the center of this configuration. On either side are 2 turbine generator buildings, and the footprint for this is about 35 acres. And that lends itself to a number of applications, and we'll talk about coal replacement in a moment. But speaking of applications, we talked a little bit about the fact that it integrates well with wind and solar because of its load following capabilities. It can also support mission critical facilities. Given that it has, let's say in this configuration, 12 modules, you can assure yourself to 3 or 4 nines, 99.9, 99.99%, to always have some amount of electricity able to support mission critical facilities. And by that, I mean hospitals, data centers, military facilities where they need high levels of reliability. Other applications can include desalination, talk a little bit about hydrogen, supporting oil refineries, both from a standpoint of providing electricity, as well as steam, process steam, for those that have steam-assisted applications in taking oil and gas out of the ground. So just a word about coal replacement. So we given the pressure that's on the fossil fuel generators and their view of replacing coal plants, we have done some studies as far as how we could retain that workforce and how that site could be reutilized in order to accommodate a NuScale SMR. There are, as we mentioned earlier, once you produce steam and you go into the power conversion system, that balance of plant should be very familiar to those that are familiar with operating a fossil plant. In this case, you're still taking steam and making electricity in the same way that you would be doing that from a fossil plant. And again, by replacing a coal plant at the existing site, you're able to utilize some of the assets that may already be in place, and you're certainly able to retain the workforce and preserve the local tax base as you look to decarbonize. Many times the coal plants are the largest employers in many communities, and having that facility in place means an awful lot to the communities, and being able to replace it with an SMR configuration is very meaningful. So I'll stop there, Julie, and I'll turn it back over to you.
Great, thank you. So we have one more short presentation. Next, we're going to hear from Simon Irish. Simon is the Chief Executive Officer for Terrestrial Energy. Simon has 20 years of global investment banking and investment management experience in New York and London. He began his banking career in London and in 2001 moved to New York. In 2010, he refocused opportunities in breakthrough energy technologies and in particular nuclear advanced reactor technologies. He holds an MA in Natural Sciences from Cambridge and a Master of Science in Finance from London Business School. Simon, we're excited to hear from you.
Thank you, Julie. Just a check on the audio and the presentation. Can you hear me and can you see the presentation?
We can and we can. Thank you.
Thank you, Julie. Well, firstly, it's a pleasure to join my colleagues today and for this panel discussion on next generation reactor technologies. So I will dive straight in with a bit of background on terrestrial energy and its IMSR advanced reactor technology. I'll start off with a statement. It's a commercial statement. It's a business statement that our business purpose as a company is to deliver an affordable nuclear power plant. And if you are to do that, you also have to do it in a cost-compelling timeframe. A timeframe which is compelling for your shareholders, compelling for your customers, the utility sector that will be seeking to deploy these systems, and increasingly compelling for governments as well that are seeking to support clean tech innovations that allow them to achieve important environmental targets. So that's our business purpose. We're expressing this business purpose in a small modular reactor power plant. Our technology choice is a molten salt technology, which is a Generation 4 technology. That power plant is called the Integral Molten Salt Reactor, and the technology and design choices of it, we believe, allow us to achieve our purpose and achieve a step change improvement in economics. With respect to our path to market, the compelling time frame I spoke about a few moments ago, we're on a clear path to market. If you are to explain where you are on that path to market, I think you also have to explain very early on how you're getting on with regulatory engagement. This is a regulated industry, a very carefully regulated industry, very good social reason. We have been engaged in a regulatory program now for nearly 6 years. In Canada, we started the Canadian Vendor Design Review process, which is operated by the Canadian Nuclear Safety Commission. We commenced that in early 2016, and we're expecting to finish the Vendor Design Review process early next year. And from a US perspective, our engagement, we're engaged with the NRC in pursuit of a Part 52 standard design approval for the IMSR core unit. And that program has been developing well over the last 18 months. Also important to comment is that if you are to, our purpose is to sell a power plant that is economically attractive to utility. You also have to talk about utility engagement at this point too. We are at this point one of 3 candidate small modular reactors that are being considered by Ontario Power Generation for deployment at its Darlington site. And Ontario Power Generation has a program of deployment where they're seeking to operate the first commercial SMR at that site as early as 2028. So I just want to talk about the connection between our technology choices and our design choices. And this represents at a schematic high level the 5 factors that drive those economics. And these are the 5 factors that allow us to achieve our business purpose of a cost-competitive power plant. We start off on the left-hand side with which is the market problem to solve today. The conventional nuclear in its current design format is too expensive for competitive markets, and that severely limits the ability for nuclear power to play a increasing role in a clean energy transition. So that's where we start. These are the 5 factors that drive economics: size, construction method, and then there are 3 factors associated with the reactor itself, with the R in SMR: temperature, pressure, inherent safety. So with respect to our system, we're small. I think a lot of my colleagues in the industry recognize that you have to make these things smaller to be financeable, but making them smaller, they may be more financeable, but you're going the wrong way down the economy of scale curve in terms of unit size. That power will be more expensive if your power plant is smaller. So that's a negative factor. You're going to offset that in some parts with using modern construction methods, and at the get-go, investing in incorporating modularity into your design, and that gives you, to some degree, offsetting economics, because you're now using the economies of scale production rather than the economies of unit size. But that probably isn't going to cover the consequences of making it small. The ability to improve the economics of nuclear power provision are associated with the R in SMR: temperature, pressure, inherent safety, and probably the most compelling one is temperature. Generation 4 systems, pretty much all of them operate hot, with high quality heat, a statement of basic thermodynamics. You have the ability to operate a machine at much greater efficiency. In our case, a 50% improved efficiency in electrical power generation, all things being equal. That means a 50% improvement in capital efficiency too. We will also have the benefit of operating at low pressure, and that eases your engineering environment, and that has capital consequences too, beneficial capital consequences to your design. And also with a molten salt reactor, you have the benefit incorporating to a really great extent the commercial benefits of inherent and passive safety that have been spoken about already, actually, on the session today. So we are the SMR in terms of those five factors. We are small, modular. We operate at high temperature. We operate at low pressure, and the design itself, the integral molten salt reactor, incorporates a high degree of inherent and passive safety. So it's those 5 factors pointing in that direction that gives us a power plant that achieves our business purpose, namely compelling reactor economics. So the key innovation here is the IMSR core unit, and this innovation is the incorporation of the primary reactor components, the reactor core, the moderator, primary heat exchangers and pumps, into a sealed and replaceable reactor vessel that has a 7-year operating life. The design principle here is that after 7 years, you replace the reactor core itself, this core unit, and bring a fresh unit in and continue operating for another 7 years, and so forth. So in terms of why a molten salt as a technology choice allows you to achieve this commercial purpose, have this economic potential, it starts off with a basic scientific statement, a nuclear engineering statement, and that is molten salts are extremely stable. They are extremely thermally stable from a neutronic perspective. They're very high stability, and they have high heat capacity as well. They're excellent heat transport fluids, and in fact, they've been used in an industrial setting today as heat transport fluids, particularly in the context of a solar thermal power plant. But that has a tremendous virtue from an engineering perspective and also an economic perspective too. You can operate hot. Operating hot, you have the opportunity to generate 50% more revenues from your power plant. That's an extremely compelling characteristic, pointing towards a much better economic position for your design. Again, operating at low pressure, because of that thermal stability, you can operate at low pressure. That eases the engineering environment and that lowers capex. And then you have the benefits of safe operation and incorporating a high degree of passive inherent safety. So the high thermal stability of molten salts leads to lower capex, higher power plant revenue, and safer operation. So it's not just about the molten salt itself. This is a design of a power plant, and it's not just the reactor itself. So here are some other design choices which have commercial consequence, and we believe attractive commercial consequence too. Firstly, this is a molten salt reactor, which is a once-through fuel cycle, no reprocessing. A once-through fuel cycle allows us to achieve our business purpose, which is cost and affordability. This is a power plant design which uses a standard level of enrichment, standard assay, low enriched uranium. That's a supply chain factor which allows us to point towards a supply chain of fuel for our reactor system in that compelling time frame, and allows us to mitigate the many risks today, commercial risks today, associated with the use of high assay LEU. The replaceable core unit, that's a design feature. That allows us to minimize the material lifetime challenges that often cited as the technical challenges to near-term commercial deployment of molten salt reactors. Not so if your design incorporates a replaceable core unit. Low pressure operation, the benefit of that is you don't have energetic sources for accidents, some engineering and some safety benefits to that. No reliance on external power for safety functions. You have a power plant that has black start capability, and that is a quite prized virtue of a power plant in terms of supporting grid robustness and stability. And the final factor is obviously the one I mentioned already, the benefit of supplying steam at standard industrial temperatures and pressures, in our case, close to 600 degrees C, and that leads to a 50% greater thermal efficiency with the Rankine cycle, and all other things being equal, that means 50% more revenues for the operator, and that's tremendously important. A couple of comments on where we are from a regulatory perspective. The NRC regulatory review is underway. We're applying for a standard design approval of the IMSR core unit under 10 CFR Part 52. In Canada, we have been engaged, as I mentioned earlier, since early 2016. We're expecting to finish the vendor design review by early next year. And we're also, with that footprint, both in the United States and Canada, we also perhaps naturally participating actively in the MOC, a Memorandum of Cooperation established between the agencies in 2018. We are engaged in the various collaborative joint reviews of our technology being undertaken under the objectives of that 2018 MOC. So just summing up our technology, our power plant by numbers, 50% improvement in the efficiency of power generation over generation 3 water moderated, water cooled power plants. The extension, quite simple extension of that statement is to say that you'll be generating less waste per kilowatt hour. In our case, we believe that to be 40% less waste, under 5% level of enrichment. And that means that we can use from a supply perspective, that means our power plant uses a standard nuclear fuel standard, which is the only one that exists today, under 5% LEU. The power plant itself generates on a full lifetime basis under 10 grams of CO2 per kilowatt hour, and we're all in the industry pretty much waving the same flag. The operating life of the power plant, it's not for 15, 20 years. The operating life is in excess of 50 years, perhaps perhaps considerably in excess of 50 years. And again, we're waving that flag along with many of our other participants in the SMR sector. And in terms of land density, 10 hectares of land can support 400 megawatts of electrical power provision. That is a very efficient use of 10 acres, and that's a flag that we're flying, and many other of our colleagues in the SMR advanced reactor sector are flying too. So perhaps, Julie, on that note, I will turn it back to you. Just final comment though, that is our IMSR 400 power plant in a positioned at a site in southern Ontario, and that's a twin unit twin reactor unit configuration with twin turbines with a generating capacity of 390 megawatt electrical. So I will finish there and turn it back to you. Thank you very much, Julie.
Hey, thank you, Simon. I appreciate that. So we got some great questions in. Push the first question to Jeff and then see if the other panelists have some information that they want to share too. Jeff, you talked about some of our challenges. You talked about the path to success. What advice do you have for some of the students that we have on the line with respect to STEM degrees and STEM education and other types of programs where they could get training to help with moving this technology, all three of these technologies forward?
Thank you, Julie. It's interesting that I get to ask that question first because I'm kind of the outlier in this whole group.
Right.
I actually started in this career as a German machinist. I actually in high school actually went through a technical training program and actually went into the trades. And the advanced career to be doing what I'm doing now with advanced reactors, which I would have never imagined back then. I recently had the opportunity to talk to some STEM students, and I said, look, I've known what I've known then, and that is having a much greater appreciation for the sciences, skills, some of those skills that I would need to actually be critical thinking or whatever, and looking at the opportunity to get some more practical experience. So there's two different routes, multiple routes to be able to support this industry. One is through the trades. And those of us that have been working with supply chain
Jeff, sorry to interrupt. Can you pull out your microphone?
Sure. So the last you heard with me was probably talking about the trades.
Yeah.
One of the needs that we have in the industry are being able to have people that have great welding skills and being able to learn those type things. Obviously in component manufacturing and machining of those type things. Non-destructive techniques such as being able to understand ultrasonic inspections. So I would look for opportunities to get some practical experience if you wanted to go into the trades and be a part of those programs, and then actually seek out from internships to actually help you get that training. The other areas on the engineering, obviously with mechanical, thermal, hydraulic, nuclear, those type of engineerings, is being able to study those. But one of the things to do is this industry is so broad now and there's such a need. It opens up a lot of opportunities for internships very early in your career development. And if you can get attached to one or more of these companies and being able to get internships and be able to work, it'll get you early practical experience so that you can be able to come in and be a long-term contributor. Anyway, Jeff's opinion. So
Yeah, thank you,
thanks.
Jeff.
Mm-hmm.
Simon, would you want to maybe add to that with your financial background and talk about maybe some of the other areas that you see opportunities for folks that are interested in getting into this industry?
Julie, could you repeat the question? Because I was sort of wondering if the audio was my end, actually.
Oh,
Yeah.
Can you hear me now?
I can, yes.
Good.
Yeah.
I was wondering, with your financial background, would you maybe want to comment on where you would give some advice to students if they wanted to come in maybe from that arena into this industry?
Yes. From there are going to be two pieces here to bring about commercial success of SMRs. There's going to be the engineering piece. There's going to be the technology piece, but there's going to be the commercial piece too. And the commercial piece, to make this these projects be a commercial success, requires the partnership of a technology with capital. It's going to be capital that drives deployment. It's going to be the return on capital that's going to attract further capital and leads to a serial set of projects and the rollout of these advanced reactor technologies across the United States, across North America, and probably across the rest of the world. So the commercial piece is going to be very, very important. On the commercial side, you must, if you are going to be involved on the commercial side, you have to have an appreciation of the technology. If you don't have an appreciation of the technology, it's very difficult to make a contribution on the commercial side. So as I have done actually in my career, I have a science degree from University in Cambridge, but I actually moved into finance, 10 years banking in London, and then moved to New York. So I think on the commercial side, for those with STEM qualifications, there are an equal set of opportunities, and I think a very bright set of opportunities given the commercial potential of these many systems today. There is going to be one or more of them that are going to be a standout success. So I think on both sides of that fence, both the commercial side, perhaps requiring some financing experience, and also on the engineering and the scientific side, there are some excellent opportunities actually for graduates today.
Thank you. Appreciate that. I'm going to move over to Peter. Peter, we have a question about what is the biggest challenge that Kairos is facing? And I was hoping that maybe you could address this both. What's the challenge today? And then what's the challenge you see moving forward? Is there something that's going to come up that you see that you're going to have to address?
Sure. And I addressed the question in the chat, but it'll be good to reiterate it. So there are a ton of challenges, and there are challenges and opportunities, right? Anytime you're endeavoring to do something that's big, there are always going to be challenges. Nothing worth doing is easy, right? So our biggest challenges include access to what's called in the industry high assay low enriched uranium. You'll hear it referred to as HALEU. It's simply a new form of fuel for those not in the industry. It's a higher enrichment than the uranium that's used today, and it's not readily available. There are a ton of efforts underway, both in the industry and on the government side, to try to address that shortfall. But I'll call it a logistical challenge at this point. It's not technically challenging, but there's a lot of work that has to go on. And we and everybody else on the call on the industry is working on that very hard. Similarly, there are changes needed to the U.S. regulatory framework. The existing framework in the United States is based on the existing operating fleet, pressurized water reactors and boiling water reactors using low enriched uranium fuel. And simply because that's the dominant design that's been deployed in the U.S. in the last 50 years, that's what the regulations and the guidance and the regulatory staff are sort of focused on. We have done a lot of work. We, the industry, have done a lot of work in the last 4 or 5 years to understand how to navigate that current framework, which is entirely doable. It's not a particularly big challenge. It's just work, but also to modify the framework going forward so it's more efficient in the future, so you don't have to do that sort of awkward navigation through the existing regulatory framework. And then public acceptance is probably the third on my list. And I made this point in the comment, and Bill Brown teed up a similar question. There is a huge amount of misinformation and disinformation out there. Under any objective measure, nuclear is the safest form of electricity production ever, and the only non-carbon baseload generation that's got any practical likelihood of deployment in the foreseeable future. And yet people are still misinformed and consequently afraid. And that's a long-term problem. That's one of the ones that, looking out over the horizon, needs to be managed very actively. Get people the facts. Stop talking so much about how safe our plants are. And that seems counterintuitive, but when was the last time you got on an airplane and had the pilot come on and say, we're going to do our best to get you landed safely, but accidents do happen. It's just not the right way to think about the safest form of electricity production ever envisioned. There are a lot of grassroots efforts, a lot of non-government organizations that have begun to advocate for nuclear in the last few years. And so we look to build on that momentum, continue getting real information out there, stop some of the disinformation, and try to make progress in that regard. And I'll make a special shout out to the younger folks and the students, especially, that are on this call. That's where you can really play a role. And when you hear somebody saying something stupid about nuclear, you can speak up and say, I may not be an expert, but what you just said doesn't sound right.
All right, Peter, you addressed that gorilla in the room for us, right? Thank you. That was brave of you. Thank you for doing that. Dom, I wanted to ask you, we got some questions about safety and safety inspections, and we, in this introduction or in our question and answer, we talked a lot about safety. We talked a little bit about emergency preparedness, and we talked a little bit about public acceptance. And those are some of the things that have caused some of the nuclear projects in the last maybe 20 years to not get kicked off the ground. So my question for you, Dom, is one of the other topics that I think we've kind of addressed, but I'd like to dig a little further in, has to do with waste management. And I guess I'm looking for some words from you, maybe about how this is different, how the advanced nuclear technologies now, and particularly your technology, would address waste management going forward.
Sure. I'd be happy to do that. I'd like to just touch on a couple of topics that were mentioned, just to add to what was already said. One had to do with community engagement. In our first project with UAMPS, which is a co-op in many ways, similar to what we spoke about earlier here in North Carolina. And we had over 200 community engagements with the local population as we were promoting that project with UAMPS, the local co-op, in order to do exactly that, provide community engagement, provide transparency to technology, and just have that openness, which I think is very important. The other topic I wanted to talk about real quick, we spoke about jobs, and I noticed there were a number of comments having to do with jobs, and they don't all need to be hyper technical, I would add. Certainly, as Jeff had mentioned, you need engineers, you need thermohydraulic people, and Simon mentioned you need folks in finance, but you also need people in the trades. And just as an example, the number of folks required to operate one of the NuScale power plants, about 270 people. Of that 270 people, about 160 only require an associate degree or a vocational degree. We're talking about plant operators, maintenance folks, technicians, training staff, and things of that nature. So it's a big tent, and there are a lot of opportunities. So I just wanted to mention that. To the point of waste management, that's a big topic, and certainly one of the questions that gets asked a lot, even in these community engagements. And so what we can say right now, as far as the NuScale product and obviously Generation 4 products are for a different solution, but from a NuScale point of view, we're using the same fuel that's being used in literally hundreds of plants globally for decades. So to the extent that our fuel is well known, well characterized, and there's a significant vendor community that is available to handle that spent fuel, and I would say it's used fuel because it still has an awful lot of potential in it, that system is in place. So it aligns very well with the NRC regulations. It aligns very well with the Department of Energy requirements. So, is there still a conversation that needs to be had about a repository, a single repository? Certainly. Is there a solution in place right now that allows for the continuation and development of nuclear energy that's acceptable, for the time being? That's also true. So I would stop there, and I'm open to questions specifically on that as well.
Thank you so much. Simon, one other question for you. What is the regulatory environment in Canada? What are you seeing from the Canadian regulators with respect to your interactions with them? You're on mute, Simon.
In Canada, the regulatory process, it follows the same set of nuclear safety principles, but it's articulating a little bit of a different process. So in Canada, you have a vendor design review undertaken with the regulator, and then you have a licensing process, which is undertaken usually by the utility that's the licensee with the nuclear regulator. Perhaps some similarity actually with the NRC, that you have a design certification process undertaken by the technology vendor, and then there will be a license application ultimately submitted by the power plant operator. But the process has differences, particularly at the vendor design review level. The Canadian process tends to be more a step process, and has historically been more risk informed and principles based. than the regulatory framework in the United States. I say historically because there are moves afoot to ensure that the US regulatory framework has the flexibility necessary for the timely licensing of these advanced reactor systems. Yeah.
And would you also, Simon, would you also maybe address the issue of waste management, particularly since you kind of have a technology that differs a little bit from technologies of
Yes.
reactors currently in place?
Yes, it differs a little bit, but in terms of waste management, I mean, what we've done as a company, very targeted innovation. We're innovating at the middle of the fuel cycle with respect to the reactor. But what we've also sought to do is to be as standard as we possibly can at the front and the back, because innovation actually is a two-edged sword. On one hand, it may put you in a very different place with respect to the economic potential of your power plant. At least potential, you can be in a very different, exciting place. But when you're standing in that place, looking around, assessing your commercial opportunities, look carefully to where you are from a regulatory perspective, and look carefully to where you are from a supply chain perspective too. You can't be too far away. Otherwise, that economic potential will always just be a potential. So with respect to the back end of the fuel cycle, we're looking to be as standard as we possibly can, and we're engaged. The first plant is likely to be in Canada, and we're engaged in defining all the waste streams associated with power plant operation in a program with the Waste Authority in Canada, the Nuclear Waste Management Organization, and the waste stream associated with our spent fuel waste stream, probably the most significant from a waste perspective. We have a program in place where that is defined. And that's important because defining on the waste side, if you want to move to the next step, which is the step with a utility who's seeking to apply for a license with a regulator, it is critically important to be able to define how you're going to manage all your waste streams. When it comes to licensing, those programs, they don't sit 50 years hence, and no one needs to worry about them now. From a licensing perspective, you worry about them now, and you represent your plans to decommission and handle all your waste streams. So that's very important. But what we're seeking to do is be as standard as we possibly can and comply with existing protocols that have been established both in the United States and Canada and elsewhere with great patience over many decades, and slot into the programs that have been established.
Awesome. Thank you so much. So let's go over to Dom. Dom, one of the questions that we're getting for the chats is recognizing the standardization as essential success factor in the nuclear industry. How many standard nuclear reactors can be economically deployed? Could you answer that from your perspective, please? You're on mute, Dom. Dom, I think you're on mute.
Sorry about that. I saw it. I would agree with what Simon said from the standpoint of standardization and trying to minimize the departure from both a regulatory standpoint and from a supply chain standpoint. I think those are very critical, and I agree with the statement about innovation, being a double-edged sword in that regard. I would say, so from a NuScale point of view, we are starting to work on 2 deployments. We have one, as mentioned, with UAMPS in Idaho, a second with Romania. Presently, that was announced last week during COP. And so our approach, at least initially, has been to utilize existing capacity within the existing supply chain, particularly when it comes to the NuScale power module. That's the biggest part. But I would also add that, at least from a U.S. point of view, and this is certainly true in the U.S., given the lack of nuclear projects over the last couple of decades, the supply chain in the United States has atrophied significantly. Many of the suppliers that we rely on, would require, as an example, an ASME code certification, which has expired in many cases because there wasn't a reason to maintain it. There's a cost to maintaining it. And so what we have been doing is really collaborating with our suppliers and our vendors in order to perform manufacturing trials, to get them up to speed, to get to a point that they can support us. And so, what might be the limit? I wouldn't hazard a guess, but I would say that success breeds success in a way. If we are able to demonstrate that this product, the NuScale SMR as an example, is a good product, a sellable product, welcomed globally, not only will we exhaust the existing capacity of the existing suppliers on the NPMs as an example, but we would justify or help them justify investment in increasing the capacity and bringing additional vendors to the table who would want to participate. So I don't think there's a limit there. I think there's a buildup, if you will, an expectation that this is a dynamic situation, and we would see additional suppliers come to the table as things progress. And I would say that across the board, with all SMRs.
Awesome. Thank you so much. Jeff, I want to come back to you. You talked a lot about supply chain and some of the issues that we have there. And we know that we're going to be building nuclear reactors around the same time we're going to be shutting down our coal plants. And when we shut down our coal plants, we're going to lose production coal ash, right? That typically goes into the supply chain to help us with concrete and cement. Have you come up with any alternatives to when that does happen? How are we going to react as an industry when the prices of concrete and cement go up due to our limited fly ash production?
To be honest with you there, that is not on the side that we've looked at from the construction standpoint. We have focused mainly on the nuclear supply chain. However, I do see that as an emerging need in being able to retool that industry and those workers to be able to provide that way. So I would probably defer to someone like Dom to maybe give a little bit more context to that.
Dom, do you have anything to add to that?
Thank you, Jeff. I think that coal ash question is actually an interesting question.
Yep.
Because you can't take the coal industry as a discrete element. We're just talking about coal. Now, coal ash is a byproduct of coal production, and the use of coal ash in cement fabrication was an ingenious way to utilize what would otherwise be a waste product. And so, are there other alternatives to coal ash that might be able to be used in cement production? I would suspect that there would be, and so that's good, presents an opportunity as well. But I think the point that you make regarding coal ash is an interesting one because, as coal is replaced, when using the analogy of throwing a pebble in a lake, what other repercussions happen as a result? That's something that I think we all need to be mindful of.
Right. Gypsum supply too. I think we should be considering that, not necessarily for the nuclear industry, but you're right. It is going to be one of the side effects of the synthetic gypsum supply coming out of our coal plants is going to go down. And so that's something as a country we're going to have to look at. Well, as a world. Peter, I'm going to go back to you with one more question. We have just a few minutes. We talked about some risks. We talked about supply chain. We talked about maybe the regulatory infrastructure. Are there any other risks that you see to moving forward with new advanced technologies?
Sure, and we've actually talked about most of them already. We could go on for days to address all of the programmatic risks associated with anything that's substantial, but the ones that sort of keep my attention from day to day are access to that fuel form, to the high assay, low enriched uranium. The issue around public acceptance is also a really important one. The regulatory framework that we spoke about earlier. Sustainability of the effort, sustainability of the support, not only on the public side, but also on the governmental side. We as a species have an increasingly short attention span, and any industry that relies on support from Congress, for example, there's always some new bright shiny object just over the horizon. So maintaining focus on the importance of this and the critical contribution that nuclear can make to clean and reliable power is going to be really important. That's a little soft and fuzzy, right? It's and it speaks to one of the things that one of the other panelists mentioned about the need for non-technical resources to support this this technology as well. Good communicators are really, really, really important. Speaking as a recovering nuclear engineer, not a lot of engineers are really great communicators. So that effort to maintain engagement both at the public level and at the congressional and other governmental levels is really important.
Yeah, I agree. And working for a utility, I can say I really rely on our corporate comm folks to keep us safe, to keep us communicating, and just to keep us from turning into too big of a nerds, right? Okay, I think we're about at the end. I really want to thank Peter, Jeff, Simon, and Dom. What a great panel. We had a rich discussion. I think we addressed most of the questions, and if we didn't, then David, I'm going to turn it back to you, and you're going to let us know how we can address those. Thanks, everybody.
Julie, thanks so
Thank you.
much. Yeah,
Thank you.
exceptionally well done, Julie, Jeff, Peter, Dominic, Simon. And with our second panel, we hear the second great challenge that we have with regard to getting beyond net zero power production. We heard the first panel, hydrogen, and the billions of dollars that need to be spent daily to achieve net zero by the target year 2050. Nuclear is part of that spend. And what you just heard are actual real projects that are progressing towards commercialization. And as we get further into the future, you're going to see that we have to have more and more and more of these. So these three project developers that you heard today are going to be prominent in the nuclear media.